device we will be looking at today is called a ball bearing motor. Its operation has been studied for more than 40 years. However, there is still no generally accepted explanation for why it works. The construction of this motor is extremely simple. Two bearings are mounted on a common shaft. Their outer rings are fixed to the supports, and wires from the power source are connected to these supports at the bottom. This flywheel here is only needed to ensure smoother and more even rotation. Now let's take a look at how this motor operates. I turn on the power source. The voltage is just over 1 volt. But since the resistance of such a circuit is very low, the motor is now drawing as much as 30 amperes of current. Let's give the flywheel a gentle push, and the motor starts to accelerate. As a result, it reaches a rotational speed of about 10 revolutions per second. I can stop it, and now watch. If I push the flywheel in the other direction, the motor will accelerate in that direction as well, reaching the same rotational speed. By the way, this motor can also operate underwater. I removed the flywheel so it wouldn't be slowed down by the water. Let's apply voltage and start it up. And now the motor can operate at higher currents because the bearings are cooled by the water and don't overheat as much as they do in air. Now it's time to move on to explaining how this motor works. At different times, different people have proposed up at least 3 alternative explanations. And we'll start with the version that was proposed in the early 70s by the well-known Soviet electrical engineers, Netushil and Polivanov. Apparently, in their experiments, they were dealing with rather large currents and observed sparks flying behind the wheel from a small contact area. And they suggested that a plasma discharge forms behind the rolling wheel, and the pressure from this discharge creates a torque that spins the wheel. Yes, of course. If we run a current of 100 amperes through our motor, noticeable sparks will fly from the bearings. But the motor will stop working very quickly because these sparks will cause erosion of the balls and rings. But if you pass moderate currents at which the motor still operates, no sparks are visible, even if you look at the bearings in complete darkness. The second alternative explanation was presented in several articles, containing a great many mathematical formulas. The authors of these articles tried to examine the interaction between the currents flowing through the rotating balls and the magnetic fields induced in these balls. However, there are 2 fundamental objections that can be raised against these theories. The first is that if magnets act on currents, then currents also act on magnets. And a ball accelerating itself is like Baron Munchausen pulling himself out of a swamp by his own hair. Perhaps this explanation could be refined in even more complex theories that consider the interaction of currents and fields on both sides of the contact area, inside the rotating ball and outside it. But there is also a second objection to this, and to understand it, let's take a look at how our motor accelerates. To record the characteristics of our motor, we installed a photogate on the same base as the motor. Let's run a current of 30 amperes through the motor. Let's start the recording. Let's start the motor. We can see it picking up speed. 8 revolutions per second, 10 revolutions per second. The speed is increasing, already 12 revolutions per second. And we can see that after 20 seconds of operation, the motor gradually begins to reach a steady speed. Now it's already 14 revolutions per second. But the increase in rotational speed, has practically stopped. In this graph, I have depicted the results of our experiment. We saw that the motor's rotation frequency initially increased steadily and then reached a constant value. This means that the total torque acting on the rotating part of the motor was initially constant and then decreased to 0. Now let's look at what the theory presented in the article says about this. It is stated there that at low rotation frequencies, the accelerating torque will be proportional to the rotation frequency and the square of the current passing through the motor. But if the torque is proportional to the frequency, then the lower the frequency, the smaller the torque, and the acceleration will not occur linearly, but will start off very slowly and then get faster and faster. And this contradicts the results of the experiment. And generally speaking, here we also need to subtract the torque due to friction, which remains constant at low frequencies. And this means that until this value exceeds the friction torque, the motor will not accelerate at all. But in the experiment we saw that it accelerates from a very slight push and then continues to gain speed. The electromagnetic theory also fails to match the experiment in another respect. In the experiment, the steady-state rotation frequency of the motor is directly proportional to the current. But the theory predicts that it should be proportional to the square of the current, which is clearly not the case. Now we move on to the third alternative explanation. The author of this explanation is usually cited as the Bulgarian dissident physicist Stefan Marinov and his 1989 interview. However, searches through various patent databases show that similar applications had been made even earlier. In particular, 3 inventors from Novosibirsk, Kosarev, Ryabko, and Velman filed such an application in 1963 and received author's certificate number 15521 for it. And all these explanations and inventions are based on the principle of thermal expansion of materials. The contact areas between the balls and the rings are very small, so the resistance of the circuit is determined precisely by these areas. When electric current flows through the balls, almost all the heat is generated in the contact zones, and they heat up significantly. The metal in these areas expands. The balls change from round to slightly elongated and become a bit wedged in place. If you nudge the motor, the balls will tilt. The heated zones will shift, and heating will begin at new contact points. So a kind of wave of thermal expansion will travel through the balls. At the same time, the wedging forces acting on each ball will no longer be aligned along a single straight line, and they will create torques that accelerate the balls. The thermal expansion hypothesis is good because it explains how the engine reaches a constant rotation frequency. After all, the faster it spins, the more the heat is spread out, so to speak, along the rim of the ball, making the heated contact zones less pronounced. As a result, the torque decreases and decreases even more as it speeds up until it equals the braking, torque from friction forces. And thus, out of the 3 proposed hypotheses explaining the rotation of the engine on ball bearings, only one remains in play, the one related to thermal expansion. Nevertheless, this is still just a hypothesis, because no theory has yet been developed that would allow us to calculate the operation of such an engine. And since there is no theory, there is nothing to compare with the experiment. Well, at least there is some plausible qualitative explanation, which, for now, is what everyone is being asked to accept. And in conclusion, I should say that we learned about this design. In 2013, when the problem engine on ball bearings was featured at the International Young Physicists Tournament. We ourselves tried to build this design several times. It didn't always work and often broke down, but eventually we managed to build a working model. And at the end of this video, we won't be asking you the traditional question. Instead, we'd like to ask you to write your comments about what you saw and share your thoughts. As usual, right below this video on YouTube.